Swayam Prabha. Digital India. Educated India.
Let us move on to a harder topic in optimization, which involves optimization with inequality constraints. Now, remember the two observations we have made so far. One is that if you have an optimization problem where the constraint is an open set, if this is an open set, then a necessary condition for optimization, which means which means a condition that any minimizer must satisfy, is simply that the gradient is. So, if x star is a local minimum, then the gradient of f at x star should be equal to 0, and if you have second order information, the Hessian should be positive semi-definite. Right. Now, if you have instead equality constraints, suppose you have minimizing this subject to equality constraint, let us say for simplicity a single equality constraint h x equal to 0, then in that case we found that the necessary condition takes a slightly different form, that you need to introduce another variable into the calculation, which is called the Lagrange multiplier corresponding to this constraint. So, we for every constraint there is a Lagrange multiplier, and so the condition then becomes something like this: gradient of f x star plus lambda times gradient of h evaluated at x star should be equal to 0. So, there Lagrange multiplier, there exists a lambda such that this is, and of course, that h of x should be equal to 0, h of x star equal to 0, right. So, so the point here is that when you are in an open set, the problem looks very different from when you are on the surface. Of course, when you are on the surface also, we were able to somehow reduce it to a problem of optimizing over an open set, but that was a reduction. But then that reduction also brought in this new quantity, which is called the Lagrange multiplier, right. Now, the problem with inequality constraints is that it combines the features of both of these problems. So, what happens when you are if you have an inequality constraint like this? Suppose you want to minimize this subject to the norm of this less than equal to r. Okay. So, what sort of region is this? So, this is these are my axis, this is my origin, this is a radius r, and I am optimizing the function f over a ball of radius r. So, the ball contains all the points on the surface of, on the shell of the ball, on the surface of the sphere, as well as all these points that are inside, right. So, if I consider a point x star here, that's inside, then and this is suppose a local minimum. Okay, suppose I write this in red. Suppose I consider a point x star here, that is in the interior of this ball, and it is suppose a local minimum of this optimization problem. Then it is also, what it means is, it is a local minimum over this a small neighborhood around it, which lies completely inside the ball. So, I can take a small enough neighborhood around x star which lies completely inside the ball, and x star is a local minimum over that, is a minimum over that neighborhood. Then what that would do is, that would then in that case the problem would sort of take the character of this problem of optimizing a function over an open set, right. Whereas if my x star is here on the boundary or on the shell of this region, then the problem would take the character of this sort of thing, because you would be satisfying h x equal to 0, or in this case norm x equal to r. So, what happens is, once you have inequality constraints like this, inequality constraints are basically capturing two conditions together. They are either saying norm x is either equal to r, or norm x is strictly less than r. Either of these is okay with us. Now, strictly less than r is basically the interior of this sphere, and that's like this problem. That's like optimizing over an open set. The one where you have equal to r is the shell of the sphere. That's like optimizing over an equality constraint, right. So, all the complications in optimization appear because of this sort of character of this problem, which sort of changes. There is a phase change that happens once you go from interior onto the boundary. The nature of the problem, the way you think about it, all of it changes. Okay. And so, what we will now build towards is ways by which you can again come up with conditions that a local minimum of such a problem must satisfy. Okay. And then using those, one can of course build algorithms for finding a local minimum. Okay. What this also entails is that we need to learn a little bit about what is called convex analysis. Okay, convex analysis, and so I will tell you what that I will introduce that subject today. So convexity is, or convex analysis is basically the study of overall shape of a region or of a body. Okay, it's not just about the local shape, but about the overall shape of it. And so for that, let's start introducing a few concepts. So suppose if I give you 2 points x comma y in Rn, this here will just denote the line segment joining x and y. So, what is that? What is the line segment joining x and y? How do I express that? Yeah, so, this is say a point alpha x plus 1 minus alpha y, where alpha can range over 0 to 1. So, as I range alpha from 0 to 1, if here is my point x, here is my point y, as I range alpha from 0 to 1, at 0 I am at y, at 1 I am at x. Okay, I cover this entire segment. So, this is the line segment. Joining x and y. Okay. Now, a set S, a subset of Rn, is said to be affine, okay, if the line passing through any two distinct points of S lies in S. Okay. So, what this means is, so if a set is said to be affine if the line passing through any two distinct points of S lies in S, means that you can take any two distinct points, say point x and y. So, these are points in S. You look at the line that passes through them. Now, can you tell me what is the line that passes through them? What should be the expression for this? The segment joining x and y I have defined above. So, what is the line passing through x and y? Hmm? Yeah. So, if I take the line passing through x and y is all points like this, alpha x plus 1 minus alpha y, where alpha is any real number. Alpha can be positive, negative, greater than 1, less than 1, does not matter. So, it of course contains the segment, but it also extends beyond x and beyond y. Okay, so, that is this line. Now, what does this what is the definition of an affine set saying? It is saying that set is said to be affine if the lines passing through any two distinct points of S lies in S. So, take any two distinct points like this x and y, the line passing through them, which is this set, it is the set of all alpha x plus 1 minus alpha y, where alpha ranges over R. This line should be in S, right. So, which means that this here, so if x and y belong to S, then alpha x plus 1 minus alpha y belong to S for all alpha. This is what this is what it means for S to be an affine set. Okay. Now, can you give me examples of an affine set? So, the entire ambient space Rn is an affine space, clearly. Any other? A plane in Rn. So, I have to define for you what a plane is first. We have not done that, but if you are just willing to just let's look at R3 for example, and look at a plane in R3. R3 is the space around us. Plane in R3 would be, say, the wall here. That the entire that wall you just extend from it to all the way till infinity, up and down in all directions. That will define for you a plane in R3. Okay. Now, is that an affine set? Why is that an affine set? So, I need to, if I take any two points that lie on the wall, look at the line passing through those points, that entire line will still be on the wall. Okay. So, that is clearly an affine set. Now, suppose I ask you, so the wall is an affine set. What about the wall and all the air on this side of it? Okay. Why is that not an affine set? Precisely. So, if I take 2 points like this, that here, take the line passing through this will go hit the wall, puncture the wall and go on to the other side of the wall, right. And so, it will not necessarily be, it is not necessarily that it is such a line will be always in this set. Okay. So, a plane, a plane that you just mentioned is an affine set. I will explain what a plane is, we have to define it, but a plane is an affine set. More generally, actually every subspace is an affine set, right. Any subspace of Rn that you take is an affine set. Any subspace of Rn is an affine set, because the subspace is always closed under scalar multiplication and linear combinations. So, consequently, so subspace is an affine set. Suppose if we take suppose we take k points in an affine set. Okay, suppose you take not just 2, but take k points in an affine set. How do you define Okay, so what one can let me ask this question in the following way. Suppose I take k points in an affine set and you say x1, x2, x3 dot 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 say xk. Okay. Now look at this sort of point. This point is summation theta I xi. Why I use the earlier notation? Let us use alpha. Summation alpha I xi, where alphas are such that they sum to 1. So, you look at this point. So, you have taken these k points which are in in an affine set x1, x2, xk, all of them in S, and consider this point. Let us call this point y. Y is defined as summation alpha I xi going from 1 to k, where alpha i's have this are chosen in such a way that they sum to 1. Now, what can you say about this point? Now, let's take two. Let's suppose I make alpha 1 and alpha 2 positive and the alpha 1 and alpha 2 non-zero and the others as 0. So, that will then capture, as I vary my alphas, that will then capture all the entire line passing through x1 and x2, right. If I take similarly alpha 2 and alpha 3 as non-zero and make everything else 0, that will capture for me the entire line passing through x2 and x3. What if I took alpha 1, alpha 2 and alpha 3 as non-zero? If you think about it for a moment, you will realize that this actually captures for you any point that lies in the same plane as alpha as x1, x2 and x3. The entire plane defined by x1, x2, x3 is being captured by you. And as you keep doing this, what you are doing is you are building, you are creating what you are creating is something what is called a hyperplane. As you include more and more points like this, eventually what you are going to create is something that is akin to a subspace. But what is going to be the property of that? It is not exactly a subspace. I'll be clear about that. But what would be the property of that? It would be such that it would be such that if you take any 2 points that lie in that set, the line passing through those 2 points will be in the set. So, the point I want to make is that if your set is affine, okay, and then you consider any k points in it, and consider a point y, any k points like this x1 till xk, and consider a point y that is defined like this by taking a linear combination which sums to 1. Okay. This is what is called an affine combination. Of the points x1 to xk which are in S. Okay. So, you take any affine combination of these points, this affine combination also lies in S. So, if S is affine, then any affine combination of points in S lies in S. That is the definition of an affine combination. So, it generalizes the previous definition in the previous case. So, in the previous case, here my alpha 1 was this alpha, and alpha 2 was 1 minus alpha. So, alpha 1 plus alpha 2 is still 1. Got it? So, yeah. So, this condition that the alphas should sum to 1 is simply is just generalizing the previous condition. So, what we are So, here what we are, the claim that is being made here is that if S is affine, then not only that the line passing through any 2 points lies completely in S, you can take any affine combination of any point, not just 2, any k points, okay, and k can be anything, take any affine combination, that entire affine combination lies in S. Okay. In fact, you can actually say the following, that S is affine if and only if it contains all affine combinations of points in S. Now, if you start thinking about it this way, you start realizing that an affine set has many of the properties that you would think a subspace should have, because if you take linear combinations of points in a subspace, that also lies in the same subspace, right. The only thing that is missing is the property of scalar multiplication. If you scale a point in a subspace, you are always in the subspace. But an affine set need not be like that. Take for example, let us draw this in R2. Say for example, here is an affine set. This is just a line. Take any 2 points on it. Its affine combination is the line itself. It lies completely. It's the line itself. So this is an affine set. The problem is that however, if I scale any point, say take a point, a vector x that lies here, and scale it. Say suppose I double the length of it. The double the length of it, that will end up here somewhere outside, that is not on this line, right. So, what is the issue? The issue is that the line need not pass through the origin. So, an affine set is actually a subspace that has been shifted. Okay. So, this can actually be shown. So, if S is affine, and say x0 belongs to S, and look at the set V. V is just the, so V depends, is this x minus x0 as x ranges through S. So, what I am doing is I have taken this set S, taken some point x0 in it, and subtracted that from all the points in the set. Now, V will pass through the origin. V contains 0. Why? Because x0 is in S, right. So, V contains the origin. So, but it is essentially just a shift of S by all vectors have been, you have subtracted x0 from every vector in S. So, you have shifted it, shifted the entire set S, but now that you have shifted it, it will pass through the origin, and it will now have the properties of scalar multiplication, of being closed under scalar multiplication also. So, V is actually a subspace. So, so an affine set is this sort of flat set which is not necessarily passing through the origin. I shift it, it will now be it becomes actually a subspace after shift. Okay, does not matter, and it does not matter what I shifted by. I can choose any x0 in S, and that's every x0 works just as well. Okay, so an affine set, you should remember, is just a shifted subspace. Now, if it is a shifted subspace, that also tells you something. Now, a subspace is always can always be given by this by the null space of some matrix, right. So, if you have any subspace, so suppose if U is a subspace of Rn, then you can always find then there exists some matrix like this A in some m cross n, such that U is the same as the null space of this matrix. So, U is the set of solutions of the equation A x equals 0, right. You can always find such a matrix. The m depends on the dimension of U. Okay, the point is that you can get you can always find a matrix A such that if you take the null space of A, that is actually the subspace U. Now, which means any subspace is the solution set of linear system of equations with a 0 right hand side, right. So, these are linear equations with 0 right on the RHS. So, now what would happen if I shift this? If I shift this, what instead of having a 0 on the RHS, what I would get is some other vector on the RHS, right. So, then an affine set if S is an affine set, then there exists some A like this cross n and B in some R n, such that S is just the set of solutions of this system of equations. Okay. So, an affine set is actually is nothing but a solution set of a linear system of equations, just written in a expressed in a geometric way rather than in an algebraic way, right.